Okay, good evening, everyone. My name is Celso Batari. This is Astro 10. So let me go over some of the main features of Chapter 5. It's a fascinating subject. It's the formation of stars and planets. Before we study astronomy, the idea we have of stars, but especially when we go outside and look at them, in the dark night sky, and then we see those dots, and then year after year they appear to be repeatable and the same, in relative positions and even coloration. If you're able to detect the coloration, this seems to be the same, not a lot of change. So we think about the stars out there as being something that is unchangeable. And uh, and ancient philosophers, by the way, they were able to develop the thought that everything up there in the celestial sphere were also perfect, because perfection implies not the the absence of need for changes, right? So if you got perfection, why change it? So if you don't change, it's because it's already complete and whole. And so these earlier philosophers, like Aristotle and Plato, they thought of stars as being something perfect, and they see them going about Earth on a nightly basis, and they thought of them as being harmonious and perfect. Also, if there is something related to perfection, if you go to these ancient philosophers, there is no beginning and end. So stars were there, unchangeable and forever, unless um, by the act of a creator, they were just poop, they came up, but they wouldn't change since creation took place. And that was some sort of a philosophical concept. Now, move all these hundreds or perhaps few thousands of years to modern time. So when we think about stars, we think about vast amount of gas and dust, and this vast amount of gas and dust populate the galaxy, our Milky Way galaxy, in a region that is called the spiral arms of our Milky Way galaxy. And and here you are seeing what I'm trying to show. It's where is my annotation? There you go. So you have this gas. It's called interstellar gas. It's not like the clouds we have in our sky, because they are much thinner than the clouds we have in our sky. But the main point is, out of this interstellar gas, if the density of the gas in certain locations is high enough, it reaches certain threshold value, then gravity forces, which we study in chapter 3, so gravity forces will kick in, and then we'll start to clump the gas, initiating a process of contraction. And as we know by thermodynamics, as you contract the gas, you force the gas molecules or the atoms in the gas to packed closer to each other as contraction takes place, to the point that collision will increase. And in physics, collision means hotter gas. So the more you force molecules into collision, so if you have gas with the molecules kind of spread out like this, they vibrate, right? They vibrate because nothing is stationary in the universe. So this vibration implies in some interaction, in some collision. But if you take this volume and you reduce, like if you packed a bunch of mice in a small volume, or if you packed a bunch of people in a small volume, they will start collide with each other. And as they collide, the temperature, the gas temperature increases. to the point that eventually a star is formed. So stars come with different colors and therefore different surface temperature. So a star that is like our sun that has a surface temperature of about 6,000 Kelvin. Kelvin is in fact is a temperature scale that can be compared with energy in physics, and that's why astronomers use that a lot in in for the solar system and for stars in general. And the temperature in Kelvin scale is equal to 273 plus whatever temperature you have in the Celsius scale. So this is a way to compare things. So the sun is about 6,000 Kelvin, and there is a very tight correlation between the surface temperature of a star and the dominant color of that star. So here's how this goes. So if you take the light the star like our sun is putting out, and you spread that light into different wavelengths, into different frequencies, you could do that in frequency as well, which means you create a rainbow of the energy, the light energy, the electromagnetic radiation the sun is sending out. What you find is most of that energy is being emitted in a region that is pretty much green-yellow, as you can see in there. So you do have some ultraviolet, you do have some infrared, right? You do have some infrared. You do have some small radio component. If you go more to the right, you have a small radio component. But the primary source of energy coming out of the sun is what we call visual. But if you, for instance, take a star that is slightly cooler, a star that has a surface temperature of about 3,000 Kelvin, that star will be peaking in the red part of the spectrum. And as you look at that star, the star will appear with a red coloration. So stars come with different colors because they have different surface temperature. So I hit this color. Which color stars would be the hottest, right? So we wrote something there. Pumbaa turned out to be smart. Yeah. Well, everything is gas for him, right? Yeah. So yeah, no kidding. Well, but I think the lion was correct as well, in a sense that he learned a tradition. It's not factual, but it's a tradition. You know, the kings, the lion kings of the past are there watching over us. It's a nice tradition, correct? So which colored star would be hottest? Correct, the blue. The blue would be the hottest. Which one would be somewhat cooler? Well, is the red one. So the more energetic would be the bluer, and then the next energetic would be the white, and then the next one would be kind of in the yellow color range, like our sun basically. And a red star like, for Aldebaran is a little bit yellow. The star Aldebaran, the eye of the bull, and a star like Betelgeuse is kind of a reddish, has a reddish coloration. So you can, in a very night, clear sky, if you have telescopes, you can point at certain stars and have a first guess on star color. Let me show you one thing quickly. Let's see if my software is on. Let's see if I can. My Starry Night software is not good. It's giving me some problem. I have to probably reinstall, but let me try to bring it again. The star Albireo we observed in the last public viewing, it's a funny star system. Let's see if I can bring it. Starry Night. There you go. Um, yeah, the stars are funny. See, the stars are boxes. I have some bug with this my software. So if I go to preferences, graphics, the star should be general. Yeah, that should be default startup appearance. Yeah, photographic is the one default. See, it's not changing. It's all kind of a box. It doesn't make sense. I think I have to reinstall this software. It shouldn't be like this. If I click default, what's going to happen? See, it's all boxes. It makes no sense. It really makes no sense. Stars are not boxes, right? So I have a bug in my software. But if we go to, um, let me see, east, that looks like this one here. This is Swan, which is funny. It's very bad. This is Deneb, and here is Alberio. See that? So let me bring Alberio to the center view and just zoom in, see if I can zoom in there. Can I zoom in? Yeah, my software is not helping. Can I see you? New options. Position. Now. Center, magnify. And see if it's going to resolve the two stars. So Alberio is a double system. Yeah, see, my software is not good. And it's all funny. I think I have to install again. It shouldn't be like that. I don't even see what's going on. The stars are not. Yeah, it's not resolving for me. Sorry about that. But Alberio, when you look through the telescope, oh, I can Google. I think I should Google. Images. There you go. So when you look at Alberio, you see something like this. It's a star that's kind of a yellowish, orange, and another one that's bluish. So it's a double system, but when you look with a naked eye, is the beak of the swan. But when you place your telescope in there, like in this one, then you can see two stars with different coloration. So just by looking at it, you can probably make a first guess on the physical properties of these two stars. So you could say, oh, this one over here is about 9,000 Kelvin, and this one over here about 4,000 Kelvin. And then you can do further investigation. But if you have to bet your life on it, that would be a nice one. Alberio. Okay. So, and then as you saw, or some of you saw, if you are taking this later, in Olenka's conference, gravity kicks in and then pull all the gas in towards the center and of mass, and the center of mass fragmentates into different clumps, and each clumps gives rise to a star. So regions of star formation are regions in which you find hundreds of these clumps, and these clumps are kind of a cocoons where a star is being formed in there. So the first time you see the star using telescopes, the star is huge, is big, is a supergiant if you think, and is relatively cold, has a small surface temperature. And as the gas keep contracting, the star eventually appears surrounded by a disk, a circumstellar disk of material, and in the center of this circumstellar disk orbiting the star, it appears the star itself. EX Lupi, there is a nice video in the internet of EX Lupi. EX Lupi is a young star that has an active disk. And so this Keplerian disk that surrounds the star, in fact, is the one responsible for giving rise to planets when conditions are good for that. EX Lupi. EX Lupi. Let's take a video. I think there we go.
The fading light of a flaring young star has shed light on a puzzle involving crystals.
So
and
see the
comets.
circumstellar disk in there? The star in the center?
Probably a pretty close match to what our own sun was like in its early in 2008, it flared dramatically in
so you see this
due to material
ring
from its disk falling onto the central star.
You see this, let me stop right here. So the star, when it's very young, the star has, in fact, the stars like the sun or low mass star, they have a strong magnetic field, and this magnetic field disrupts and breaks this disk. It's so important. It's so energetic, then that it stops the disk accretion onto the star and creates this hollow, this gap between the star and the disk. And the magnetic field itself guides gas from the disk onto the star. And then you can see this kind of in animation that is being shown here. See that? This is driven by magnetic fields basically. And then eventually this gas falls in certain regions in the stellar atmosphere, and when the gas falls in there, it creates shocked regions where the temperature is slightly higher than the average surface temperature, and then they start flare up a little bit. In this particular case, EX Lupi, they found evidence of olivine in the circumstellar disk. And olivine is a mineral that can be formed here on Earth on magma chambers at a high temperature, about 2000 Celsius. But it was a puzzle how you find these crystals, these minerals, in fact, in around the stars. And the best explanations they gave was UV radiation, ultraviolet radiation, that is produced when this material falls on the star, creating the shock regions. So the ultraviolet radiation is the one providing energy to initiate a crystallization process of olivine, and then you can see that olivine in this curve right here. See that? So when the star was not flaring, you have just the spectral signature of a star. But when it starts flaring up, there is a very tight correlation of some bulging in the light distribution that indicates the presence of olivine. So that's one of the wonders of spectroscopy. You don't need to go to the circumstellar disk and collect materials and analyze in the laboratory. You just use light for that purpose. That's what we, in fact, studied last week, the importance of light in astronomy. Okay, oops. Sorry about that. Oh, sorry about that. Okay. Spelling. What do you mean by spelling? And there you go, the contraction process, right? So eventually the circumstellar disk rotates and falls on the star. And as Professor Olenka mentioned in her talk, the star speeds up and spins up as a result of this transfer of angular momentum onto the star. And one of the things that happen too is since the star has its own mechanism to avoid being disrupted with so much rotation, in this early age of star formation, the star loses lots of material, especially in a phenomenon called bipolar flow. Bipolar flow. So this bipolar flow is you have circumstellar disk, you have a star in the center, and there is an ejection of material in a direction that is perpendicular to that of the rotating circumstellar disk. Okay. Brown dwarfs are stars that they don't have enough material to ignite fusion reactions of hydrogen in their very core. So as the star collapses, its density, what happened with the density increases. And the temperature increases too. So the brightness, now here's the thing, when the star, when the temperature increases, there is something interesting here. The star collapse, right? This is correct. The density increases because now you are contracting the gas and forcing the gas to be in a smaller volume. The temperature, as a result, increases because the star becomes slightly hotter. Now, here's the thing. So the brightness, I don't know. Based on the options here, since the first increase, the second increase, you should go to increase. But I kind of cross this out. I don't agree much with that. I mean, I didn't create this question. Because see, as the star diminish its volume because it gets smaller, the temperature increases the brightness, which is the amount of energy the star is emitting per square inch. So if you define brightness as that, it is true, the brightness of the star increases because you are emitting more energy per square inch. So if you measure 1 inch and another inch, so there is more energy coming out of that square inch. But since the star is smaller, so altogether the area of the star is less than it was when it started its contraction process. And as a result, you might, yeah, you mentioned well the Stefan Boltzmann law, that the total flux of a star is 4 pi r squared, which is the radius of the star, times a constant times the temperature to the fourth power. So when the temperature increase, so this factor here increases. which means your square inch will produce more energy. That is true. But we shouldn't forget this quantity here, which is the radius. The radius diminish, and the radius is which determine how much brightness the star itself is showing. Which means if you are observing a star with a naked eye and you could allow the time to go fast, like in millions of years, and just roll the movie and see what would happen in a time scale of 20 million years when the star start out its life as a huge subgiant cold pre-main sequence star and initiate its contraction to a final main sequence star, which we are going to study um, next week. So if you could observe that, because the star contracted, um, you um, you would observe, in fact, some decreasing in apparent brightness because the total emitting area would diminish as a result of contraction. Okay, so it's interesting that you mentioned the Stefan Boltzmann law, which really mentioned that. So if I were writing this question, I would first be more clear how I define brightness, and I would put in decreases, not increases. I would write decreases. See, I don't agree with that answer, so I have to take that out. I think Olenka showed this picture. Here's an example of a central star surrounded by a circumstellar disk like this, and the bipolar flow. Here's the bipolar flow. Okay, another example here. So that's the circumstellar disk and the bipolar flow, the flow in two directions. See, and there are several. Oh, I think Olenka showed that picture. Okay, more bipolar flow right here. See that? Cha, cha. It's funny, you see this mechanism always also happening as bipolar disorder. Oh, that's why they don't have enough lithium, huh? Yeah, no kidding. The lithium abundance is not that great in stars, so that's why they have a bipolar disorder. That's funny. Well, that's probably not. I might get in trouble. But anyway, so this bipolar flow um, is also observed in galaxies when galaxies form. In fact, this model of an accretion disk giving rise to young stars was published in 1974 by Lyndon Bell and Pringley, two astronomers. One is in UC Lick. I think he's still active. Um, no, no, I'm making confusion. No, I don't know if they are active, and I don't think they are in UC Lick. But they apply this model to the formation of star, but also formation of galaxies. So in galaxies, the volume of gas is much bigger than that one, right? And instead of having um, little clumps of gas formed or little edges and swirls that might give rise to planet formation, in the case of a galaxy, you have formation of um, structures such as globular clusters. Um, and you have the bulge being formed. You have a major structure, but also this bipolar jet. And you see this bipolar jet when we studied galaxies formation towards the end of the book. You're going to see basically the same idea. These gigantic radial lobes, and these radial lobes associated with radial galaxies are the result of these energetic jets. They are decelerated, they are slowed down by interstellar gas, in fact, intergalactic gas. and creates a bow shock. And but the physics is basically the same. Is the physics of gas that contracts, that forms, in this case, stars, in the case of galaxies, and eventually give rise to bipolar flow. So planet formation. So planets forms and by accretion, basically. Olenka presented the two mechanisms. The one the book emphasized the most is the classical one, in which as the temperature in the circumstellar disk drop down, there is accretion in which atom by atom are collected by certain nuclei and forms crystals, right? These crystals give rise to grains, and electrostatic force adds more ions to it, to the point that eventually you form dust, you form grains, and these grains will stick together, growing in size and eventually forming the so-called planetesimals. So when you look at our solar system, in the region between Mars and Jupiter, you do find these millions, if not billions, of planetesimals, which we call asteroids, which represents the material that were pretty much populating the circumstellar disk around the Sun at early ages of solar formation. Because the Sun, as the Sun contracts, it gets hot. There is something interesting that happened, and that will determine what type of planets will be formed in the solar system. And what I'm mentioning here is pretty much the classical approach to planet formation. So as the central star forms, the region closer to the star is getting hotter, right? Because you have the star right there. So this region is hotter than the outer skirts of the disk. Which means because of this heat, closer to the Sun, the temperature is not cool enough to allow for ice formation. So it's not a good region for volatiles because it's too hot. But you might have enough temperature to initiate formation of certain minerals and certain crystals, as in the animation that I just showed. What did you say there? Accretion outside, gas collapse inside. Accretion is happening all over the circumstellar disk. We have accretion all over. I mean, the gas in the disk spirals and then falls onto the star. I mean, that's what is called Keplerian disk. Now, this Keplerian disk initiated its collapse, and if you apply the laws of the dynamics of this disk in the very beginning, it has an expansion, an overall expansion, as it accretes onto the star. So it starts with a few astronomical unities and grow to hundreds of astronomical unities when the process of accretion is completed. But basically, the heat in the central star will vaporize, or you will not allow crystallizations of ices, of volatiles. So in the region closer to the star, to the central star, you might have a large concentration of iron-rich minerals, of carbonates or silicates and mineral oxides. And as you go to regions further out with lower temperature, you have those as well, but also you have ice formation. So the physical characteristics of planets in these classical models ended up being somehow controlled by, excuse me, controlled by the Sun or by the central star because essentially of its temperature. Okay. um, atmosphere, the so-called primary atmosphere. Primary atmosphere is any light gas that happen to be populating the nebula, and and then we are pretty much talking about something with hydrogen, something with helium. Those are the those are the abundant gas populating the accretion disk. So when planets are formed, so the atmosphere, the primary one is basically that. But as the planet cools down, so volcanoes and volcanic activity kicks in, and then as the surface, as the planet surface crystallize and harden, and volcanic activity start, one of the main components of volcanic emission, the gas that comes out of volcanoes, is carbon dioxide vapor, which is another way of saying water. So carbon dioxide, water, and you have other gases, but those are the two primary ones. They will now be um, the main the main part of them. They will provide the larger percentage of gas in the atmosphere will be primarily carbon dioxide and and vapor. Now, as the temperature cools down even further, now this vapor condensates and then falls in a. Wait a second. What?
Night.
Good night. You're going to sleep.
Mm-hmm.
Okay. Good night, baby.
Night.
It condensates and then it rains down. So we are talking about primarily a raining season that occur here on Earth. I mean, of course, because we have oceans and we have a hydrologic cycle, but also on Mars. Oh, please, Harry, you're the only one there. Do not miss The Martian. It's fantastic. It is fantastic movie. It's phenomenal. The graphics are phenomenal. The landscape is phenomenal, and the acting is very good. It's funny. There are jokes here and there, and you shouldn't miss this movie. It's very good and very well written. You love it. The Martian. I think they opening October 1st. So, in our planet Earth, this raining season um, that lasts when the planet was cooling down, and again, the rain was pretty much the result of volcanic emission. Next weekend, yeah, good for you. Yeah, go, don't miss. It's very good movie, excellent movie. You should go. Um, so uh, when the raining season starts for a long period of times here on Earth, this rain washed out most of the carbon dioxide lying in the atmosphere, and now we have. Oh, by the way, another volcanic gas important that I didn't write was nitrogen. Nitrogen is important too. So nitrogen, carbon dioxide, vapor, but it's in more percentage. The higher percentage is carbon dioxide and vapor. So eventually, this rain washed out um, a large percentage of carbon dioxide, creating carbonic acid, and now we have life kicking in the oceans, and then we have little marine creatures using the carbon to build up their organs and skeletons, and these marine creatures die. So we have a cycle of life and death, as always. And these little marine animals rain down to the bottom of the oceans, and then they form what today we call um, limestone, limestone, marine limestone. And if you go to the Rockies, all those limestones existed a long time ago in the oceans as little crawling creatures or marine animals. So let's just keep on going here and see if we can get down. And exoplanets. So exoplanets. So Doppler effect is a technique that we learned last week. And what happened is basically if you have a light source, that is emitting on certain wavelength, if you observer are moving towards that light source, or if the light source itself moves towards you, you perceive those wavelengths at that light source at smaller wavelength, which means you will observe a slight increase in frequency. So we call this blue shift. So the light shifts from towards the blue. If, for instance, the source of light moves away from you, or you are moving away from the light source, so basically Doppler shift is based on the relative motion between the source and observer. So if the relative motion is such that observer and source move towards each other, the observer detects a blue shift. If they move apart, the observer detects a red shift. Okay, as in this example I'm trying to put in here. So if you have a big star, and orbiting this big star we have a Jupiter-like planet, as the planet, see, I can't do this, I don't know why. As the planet orbits the star is gonna wobbles, in the space. Like if you have two sources of mass, if they are comparable in mass, they're gonna be orbiting this so-called center of mass, right? Something like that. And then, but basically, you are going to see this star system wobbling in space. The motion of the star is very negligible, but not enough to fool spectroscopy. So spectrometers can detect, if they are built to detect high precision, they are able to detect this little motion, and that's was basically the technique used to detect planets like Jupiter-like planets orbiting stars. Another technique is photometric. The photometric technique is based on a planet that as it transits the star, it eclipses some of the star light, because now that starlight that otherwise would go towards observer is trapped and absorbed by the planet itself. So, which means you detect a dip, a little fall of that total brightness. And astronomers can use not only the length of this transit, but also the depth to figure out the relative size of the star and the planet. And pretty much that's it for this chapter. It's a good thing. I recommend you guys go through the astronomy action video that explains Wien's law, which relates the peak of the brightness with the wavelength or with the stellar color. That's what I showed in the very beginning of this lecture. But this chapter is fascinating. Good enough? Okay. Good night to you, man. And good night to you all.